While computing capability has advanced rapidly on Earth, onboard computing in space is more complex, as chips have to be hardened to function amid the radiation environment in space. Edward G., co-founder and CEO of three-year-old startup Aethero, is working to tackle this challenge and enable higher computing power on board satellites. Ed explains some of the challenges with space-based computing and why there's a push to improve onboard processing to support missions like space missile defense, space domain awareness, RPO operations, and even future targets like orbital data centers. He sees the space industry in the midst of a transition from where onboard processing will become the default rather than the exception. I'm Rachel Jewett, and you're listening to On Orbit, the podcast that asks, what's our future in space? Hi, Ed. Welcome to On Orbit. How are you doing today?
I'm doing fantastic. How about you?
I'm good. Yeah, thanks for joining. So earlier this year, your startup, Aethero, raised its seed round, and you guys are focused on space grade computing. So I'm excited to talk with you and hear a little bit more about that.
Got it.
Yeah, just to get us started, tell me a little bit about yourself and what led you to co-found the company.
Yeah. So I actually started Aethero after dropping out. I know that's a pretty common theme in Silicon Valley nowadays. Like in San Francisco, I think the average founder now is like probably like what 22, 24. I don't know, but everyone seems to be dropping out, following in the example set by Mark Zuckerberg, the most well-known of the dropouts. And I was no exception, right? And one of the biggest reasons why I dropped out was there's always this insatiable want to solve a problem, to work on what you believe in, to work on what you really you see a problem and it drives you, right? And that's how Aethero came to be. I remember look like Moore's law. Everyone knows about Moore's law. For everyone from NVIDIA to Intel, all the big chip companies, all the fab companies, all talk about it. And for those that don't know, Moore's law is that the progress in computing technology gets exponentially better. I believe it was every 7 years, and this means that chips become more and more and more capable, and something you can see on Earth. You compare a computer from the 2000s, and then you compare that to a computer today. You compare a chip on, let's say, a flip phone to the latest iPhone, and it's like these devices came from entirely different centuries almost, right? Because the capabilities that we have in computing technology today that brought us AI, that brought us like the digital economy, that brought us unprecedented levels of connectivity. That technology was seen as impossible, completely impossible, just as early as like 30 years ago. But whereas computing on Earth has advanced so greatly, it's not the same in space. To give an example, NASA's Perseverance rover on Mars uses the RAD 750, which in turn is a version of the PowerPC 750, which was used on the iMac in 1998. Now, people might ask, well, why doesn't NASA use the latest and greatest chips, right? Well, like imagine if the Mars rover, instead of using a chip from 1998, had an NVIDIA RTX 5090 GPU on it. Imagine what it could do. And I was one of the people to ask these questions. And like oftentimes it becomes, yes, you could use the latest chips, right? But you want resiliency, you want redundancy, you want error correcting code because they're sending these missions out and they have to work. They absolutely have to work in deep space for decades at a time. So then the question becomes, well, how do we make them work? How do we take these latest chips and then make them work and then make that process of space grading them and getting them flight heritage fast enough so you can constantly keep up the new chips being released every single cycle? And that ultimately what Aethero is all about.
How are you looking to solve that problem? Are you taking existing chips and making them space grade? Is it making new chips? What's your solution?
So that's a really good question. So there's two approaches to this, right? You can make your own chips to have them work in space, or you can make your like take existing off-the-shelf chips and then essentially space grade them.
Hmm.
We believe. I believe there's merit to both approaches. The first approach is very tempting, right? Like existing chips aren't exactly made to work in space. The thermals aren't the best for operation in a vacuum. They don't have the best design when it comes to mitigating radiation upsets, to mitigating latch ups. They don't have the best redundancy. They're meant to accelerate computing tasks on an Earth environment. But at the same time, there's limitations to that. One of the biggest limitations is that the market for a space specific chip will never be as big as the market for a terrestrial chip. And this means that even if you go out today and you make a chip that's specific to space and has all of the capabilities of an existing chip like let's say NVIDIA RTX 5090 GPU. In 10 years, the NVIDIA chips are still going to become more advanced because they have more capital coming in because the market size for terrestrial chips is simply so much greater. They have far more capital to invest into new advancements, they have far more capital to invest into manufacturing, whereas with space-grade chips, since the market is so much more limited, NVIDIA probably sells more chips in a single month than we have will launch satellites this decade. Since the market is so limited, it greatly constrains the amount of resources you can invest into this while still keeping up with the latest advancements. Then we go into the next approach, taking terrestrial chips from Earth and then making them work in space. Now, existing approaches have really gone at it two ways. One of them is hardening the software, right? You have error correcting code. You have different software programs that mitigate bit flips that help restore corrupted memory and handle errors and radiation-induced glitches. The second option is to harden it on the hardware standpoint. And what we ultimately found out was you have to do both, right? But because you have to harden the chip to protect it against long-term TID damage, as well as finding ways to harden the chip's memory itself from bit flips, while at the same time, you also need to develop the software that enables the chip to survive for long periods of prolonged operation in space. And this essentially gives the customers a solution that's optimized for space operation from both a hardware and a software standpoint, which provides a much more resilient product at the end of the day. And that's the approach that we ended up starting off with.
Yeah, yeah. Do you see obviously there are challenges with chips that work and have that resiliency and operate in the space environment. Do you see the challenge as there aren't enough providers or there's a shortage of products that work for the market? How do you see the challenge?
I wouldn't say the challenge is in the lack of availability. The space industry is known, rather famous, for having quite a poor supply chain. Like there's stuff, I know for a fact that there are components on buses or propulsion units or sensors that have lead times measured in years. And the chips don't really have that same level of constraint. I would say the challenge for space computing actually comes in finding market application in one, convincing users that, hey, look, you can take these latest and greatest chips, they work on your spacecraft, they can work on the spacecraft without causing faults, without causing errors, without compromising the success of the mission. And the second biggest problem uh, comes from the roadblocks of existing chips because there's only so much you can do to harden terrestrial chips for operation in space. They aren't intended to operate in space, or essentially duct taping, proverbially duct taping a solution together. And for chips in that means ultimately, if you want the best chip, I'm trying to say, if you want the best solution that can work on, let's say, a multi-decade interplanetary mission, you need to have a specific space-grade chip. But the market for that just isn't big enough to justify such a chip existing without significant R&D expenditure from the existing large government organization, from existing large space companies or large space commercial players. And such a chip either won't exist for at least the next couple of years, or if it does exist, it will likely be something that's completely proprietary to a singular ecosystem.
Interesting. So then tell me a little bit more about starting Aethero. How long has the company been around and what has your experience been so far?
So the company is 3 years old at by this point. We are well, you say we're a young company. Well, I can't say that anymore. We aren't really a young company anymore. But it's been one hell of a journey. It's We started the company in a basement. We built the first demonstrator. We built the first prototypes in a basement. Apple started, I suppose that's the theme for any great computing company. Apple, after all, started in some Palo Alto garage. Well, we started in the Midwestern basement. And from there, we it's space is a tough market. There's been lots of ups and downs in the history of the company, but all I can really say is I'm proud of what we've accomplished. I'm proud of what the team has been able to do, given the limited resources, given the constraints of the space industry, and given the difficulties of operating in space environments. And we've been able to get flight heritage for our hardware. We have multiple missions going up, and we also have uh, one of the best teams out there when it comes to space grade computing.
Yeah, you said in a Midwest basement. Where in the Midwest?
Michigan.
Okay, cool. I'm based in Cincinnati, Ohio, so I'm in the Midwest.
I say, well, if you're an Ohio State fan, I'm afraid we can't get along.
To be honest, I'm not. I'm not. No worries
That's
there.
good.
Yeah. Where do you see this, the benefits of more capable chips on board spacecraft for more onboard processing? How do you see the benefits of that? Why do we need better chips in space, is what I'm trying to ask.
Now you're starting to sound like a venture capitalist. So, right. Defense, right? Defense is by far the biggest and primary use case of what we're doing. Right now, the government is pushing towards programs like Golden Dome, programs like the prolific PWSA. If you want to have the ability to detect high velocity objects such as ICBMs or high velocity objects such as other spacecraft in space, and to be able to classify them and take the appropriate actions in a relevant time frame, then you need the ability to have onboard computing. You can't wait for your satellite to pass over a ground station, send a command to some room in the Pentagon, have that room come up with the decision, and then uplink that decision back to the satellite. By the time you do that, it's already too late for you to take any action of significant, any tangible action. And I know there's a lot of talk around the Earth observation industry for space-grade computing, like on process data before it gets sent down to the ground. Yes, there is a market for that, but it is more limited than one might think, right? Because, well, I mean, look at commercial Earth observation, if I might point that out. A farmer doesn't care if his image of his crops was processed and sent to him this day or this month. And likewise, for a lot of commercial users, like construction companies, for example, or hedge funds, they don't really need that specific fidelity, that specific fidelity in terms of time when it comes to receiving data, process data from space. But when it comes down to the Department of War, every last second matters when there's lives on the line, when there's American assets in space under threat, under attack by Chinese or Russian adversaries or near peer adversaries. And this means that there's a massive, massive push for better onboard computing in in these applications because better onboard computing is better missile defense, it's better space domain awareness, it's better RPO, rendezvous and proximity operations, and these are all fields where the Department of War sees as absolutely necessary to assure American space supremacy.
Yeah, we're absolutely seeing a push for more capabilities in space, like you said, like more advanced RPO, these things that are going to need more advanced onboard computing. But it's interesting, and you were talking about the limitations of downlink and the amount of time it takes to get the information. And I feel like there are people are looking at that problem in a number of ways, whether that's moving to computing on board the spacecraft or whether it's intersatellite link relays. Um, just interesting ways of looking at the problem of trying to get that data down to Earth faster.
Yeah, so been quite interesting because you have new players like Starlink entering the market. I believe of Elon Musk announcing now that V3 satellites will carry GPUs. So you have intersatellite links happening. You have Northwood Space, whose idea is to proliferate ground stations more. So you have more channels to bring data from space to the ground. And then you essentially have our solution, which is processing the data in space. So we can send downlink more in every ground station pass. And ultimately, I think all of these solutions do work together. They do synergize to form a space data highway, right? Like the internet doesn't exist only because of internet routers. There's large amounts of infrastructure that go into global internet, into ensuring global internet connectivity, and that's going to be the same with space.
I like that idea that it's all part of the space internet highway. That's a I like that idea. So tell me a little bit about your flight heritage and demonstrations so far.
So back in August, we launched our first satellite carrying the first generation computer. It was based on NVIDIA Orin NX SOM. Funnily enough, we actually beat Planet Labs to it by 3 months. I know Planet likes to claim to have the first GPU in space, but theirs launched, I believe, in Q1 of this year. We launched in August of 2024. So take that, Planet Labs. Uh, but yeah, so that was the satellite is still operational today. It's still in orbit. Alongside Flight Heritage, we've also done extensive simulation work alongside a very intensive testing campaign at facilities like HIMAC and Triumph with our partners, Cognitive Shielding Corporation and the Air Force Research Laboratory. And this Flight Heritage, this lab testing data has given us very, very valuable insights into how chips work under different radiation conditions in space, how they work given across different lifespans in space, and not only how do our chips work, how do our computers work, but also how does our software operate under different scenarios that they'll face in an orbital or deep space environment.
Interesting. Did your company build the bus for your spacecraft? Did you work with a partner? How did that work?
We bought the parts from Endurosat. We
Okay.
assembled the parts ourselves, and we did integration ourselves, and we launched it. ourselves and is operated by us. One thing that we've done is we operate all of our missions in-house, and we try to get as hands-on with integration and assembly as possible. I know a lot of space like people might ask, why don't you ride with someone like Loft Orbital? Why don't you do a rideshare payload? It ultimately comes down to strategy, right? The Department of Defense, notably, does not work with component manufacturers. We don't, and ultimately, we see our solution as being able to work with multiple bus manufacturers and convert them into high compute, buses for autonomous use cases or use cases where there's a great need for the buses to function autonomously in orbit, and then work and then use these as our own way of becoming prime by angling space computing as our competitive advantage. We don't want to be a component supplier forever. And as a result, we don't see that much value in rideshare missions, at least for ourselves.
Yeah, interesting. Um, okay, so is your plan to work with different bus providers and you're providing the computing aspect, or what's the go to customer strategy?
So we work with different bus providers. We white label the buses. We integrate our computing products onto the buses. It's not, and people might ask, well, aren't the guys just selling an edge computer on the bus? And yes, and no. No, in the fact that our we don't just sell edge computers, right? We have expansion modules that have functionalities to functions in OBC. We have SDR expansion modules. We have FPGA expansion modules for high-speed communications between subsystems on the bus and for working with in- data-intensive payloads. We're working, our systems can be put into distributed clusters. So instead of having one edge computer, you can have a whole computing cluster of multiple computers on the same spacecraft. And that essentially enables us to go from a simple space edge computer company to an actual full-blown space computing company that can tackle all of the technologies from the edge to in-space servers and potentially even orbital data centers as well.
Orbital data centers. That's been a kind of a hot topic in the past few weeks.
Yeah, everyone loves orbital data centers. There's been a lot of talk around because everyone is very cognizant of the issues faced by hyperscaling AI infrastructure on Earth. And this
Yeah.
obviously uh, reason for that, right? Like data centers use so much water, data centers use so much power. I'm less concerned about the water aspect. Everyone knows, everyone should know the water cycle by now. I'm surprised that water has become such a contentious issue. But the other contentious issue, which I do agree with, actually is power. Utilities infrastructure in much of the United States is poor. Poor is an understatement. A lot of the utilities infrastructure wasn't even built this century. And when you start putting, let's say, terawatt or gigawatt scale data centers into these areas that have very poor utilities infrastructure, what happens is that in the best case, the utilities bills of everyone in the area spikes. And now they're all mad about the data center that just moved in. Or you start browning out the neighborhood. And now they're still mad about the data center moving in. And ultimately, there's going to be a tipping point where people start to realize, yeah, like it's quite difficult to shove data centers into the overburdened utilities infrastructure that we already have in the U.S. Electrical generation capacity isn't going up as well. Like we're nowhere closer to building the level of nuclear power or solar power that we need to operate these data centers on Earth. So a lot of people are looking to space, but personally, I think that's more of a problem for the 2030s, 2040s. Uh, there is a need today, and that need today is in processing data that's generated in space, because all the friction right now for orbital data is moving that data from the space layer down to the Earth layer. And the more we can do in space with that data, even potentially handle it all the way from input raw data all the way to response, the easier and better it is to operate your mission.
Yeah. Tell me about your experience raising the seed round this year and what this new funding will allow the company to do.
Got it. So technically, we didn't raise it this year. We raised it last December. I announced it in June of this year because I realized that if I didn't announce it then, I would actually never get around to announcing it. And the seed round ultimately comes with several massive goals of mine, right? We have two more satellite missions planned, carrying uh, our next iteration on our Orin NX SOM edge computer with a multispectral imager.
Mm.
We have our third mission, which is an ESLA-cast mission. I unfortunately can't reveal much more than that, other than the fact it's validating our next generation module based on the AGX.
Mm.
Uh, and we also, on top of that, we have the full build out and release of our expansion ecosystem with the SDR functionality, with the SDR modules, the OBC modules, the FPGA modules that I've mentioned before, for supporting every single possible mission that a customer may come to us with. And we also, on top of that, uh, have the release of our software ecosystem that does everything from schedule enabling users to seamlessly schedule over the air updates to model updates to the satellites on orbit to enabling them to automatically train, annotate, and build new models based on the raw data that their satellites are collecting. And ultimately, our goal to build entirely self-contained software and hardware ecosystem that can integrate seamlessly onto any satellite mission.
Yeah. What's been your the industry response since you announced the seed round?
It's been quite positive. We're working with several large space companies. We have actually our first computer launching for commercial customer at the end of this year. And if anything, we've been more overwhelmed with demand than we can handle. Right now, our production backlog is significant, and it's been actually our biggest struggle this year. Surprisingly enough, is actually making sure our supply chain was able of sustaining larger volume orders from customers than we had originally anticipated.
Yeah, I was curious about that as well, of supply chain challenges that you guys would run into.
Yeah, the supply chain is always a finicky thing, right? The space industry has a fickle supply chain, and oftentimes it's made worse by the fact that you have to trace every single component for your supply chain. Like, for example, we're ASI 100 certified, and this means we have deep visibility into every single level of our supply chain. And when you have so many suppliers, you have so many components, you have so many circuits, you have so many places, and you have a whole process for tracking every single component, all the way to manufacture and final completion of the product. And then you have to manage the quality, and it's a ton of overhead. It's a ton of tons of paperwork. And quite honestly, I would recommend that any space company get a dedicated supply chain engineer at the moment they get the chance.
Yeah. What about navigating the almost everyday changing tariff situation this year?
So we don't really manufacture. We don't use foreign parts.
Okay.
We've been shielded from the tariffs mostly by the fact that we sell heavily to the DOW, to DOW primes. And this does mean that we were shielded in a way, right? But at the end of the day, the tariffs have increased the costs of raw components, and we've seen that hit our supply chains. We've seen that hit via inflation, but it hasn't been drastic to us. I know like some companies have completely knelt over from the tariffs, but we haven't really had that drastic of a reaction.
Yeah, okay, that's interesting. Um, do you see is are you trying to bring like do you see NVIDIA as obviously they're a giant in computing? Are you like a small scale competitor to NVIDIA? Are you a partner bringing them to the space industry? What is maybe not your direct relationship with them, but just how do you see that?
Direct competitor with NVIDIA? Oh God, no. I can't imagine that. But close partner bringing in to the space industry, yes, right. We are like we were one of the first space companies to enter the NVIDIA Inception program. We've been closely partnered with NVIDIA since then. We've received level of technical support from NVIDIA when we've needed it. We've done work with NVIDIA before, collaborative work for our customers. And NVIDIA Ultimate is one of our closest partners today, and a partner that we're very proud to work with, right? Given the massive strides that they've made, the amount of work that they've done in pushing AI to the forefront of the modern economy.
And then, how do you think that greater onboard computing capabilities will transform how satellites are operated in maybe the next 5 years?
That's a good question. Ultimately, I do think that space compute, like whether or not the satellite has some level of payload processing or onboard processing, is going to become the default rather than the exception, right? Like even with modern satellites, you're seeing more powerful CPUs, more powerful FPGAs being launched on even like satellite buses, and this I do think that's going to become more and more common, and even and what I also think will become more common is the proliferation of GPUs as more like our competing options mature in the market, as we get more flight heritage, and also as other alternatives to us also are emerging on the market as well. As I'm less interested in what we can do for existing use cases, but more interested in what we can do for future use cases. Use cases in space mobility, such as on-orbit servicing for space tugs, fuel tugs, all of that needs a great deal of space computing if you want to run that efficiently, and if you want to run, like, for example, regular fuel shuttle flights between a customer satellite and a fuel depot. You'll need onboard great computing for what you want to do with missile defense, missile warning, missile tracking. All of that needs a great deal of onboard computing. You'll need onboard computing for what NASA wants to do with the Artemis program, for establishing a permanent human presence on the moon. Human civilization right now is ultimately built on computing power, and you can't really rely on data centers all the way on Earth when there's a 3 second light delay of transmission all the way from the moon to Earth. So you need computing power locally on the moon as well for the rovers, for your landers, for the machinery that are operating. So ultimately, when we look towards the future, we see more future use cases coming down the pipeline for onboard computing, especially as launch prices and launch costs start coming down. And that's what we're more excited about.
So, tell me kind of what some of the next milestones that you're working toward, and if you have any final thoughts as we wrap up.
So the next couple of milestones, we have our second satellite launch next in February in 2026, followed by our third launch of an ESPA in the summer. Both of these are extremely exciting milestones, since we'll be bringing our computing, bringing our products to capabilities that have not yet been demonstrated before on orbit. Another massive, very thing that we're really excited about really is the work that we're doing with customers. I can't talk too much in detail about them, but our customers are doing fantastic work, and we're very, very excited to be supporting them along in their missions as they tackle everything from Golden Dome to the Artemis program.
Well, Ed, it's been great to talk with you, and best of luck as you are getting ready for that February mission.
Thanks. It's great coming on here.